Digital multimeter principles. A digital multimeter, DMM, is an electronic measuring device commonly used for troubleshooting electrical and electronic circuits, equipment, and components. DMMs can perform more than one function. For example, when measuring volts, a DMM functions as a voltmeter. When measuring amps, a DMM functions as an ammeter. DMMs are selected for specific applications. Standard DMMs are used for basic voltage, current, and resistance measurements. High-performance DMMs are used for troubleshooting more complex problems, such as improper frequencies or momentary problems. DMM accessories are used for special applications, such as measuring temperature. For maximum safety and efficiency, a technician must be familiar with fundamental DMM operating procedures. Meter abbreviations. Meters use standard abbreviations to represent a quantity or term. Quantities such as voltage, current, and resistance are identified by their abbreviations on meters. Terms such as minimum and maximum are abbreviated to min and max in order to save space. Abbreviations can be used individually or in combination with prefixes such as millivolt or milliamp. In addition to abbreviations, meters also use symbols to display information. Most meters use standard international symbols that represent an electrical component such as a battery or diode. Symbols also represent terms such as ground or positive, or messages to the user such as warning or see handbook. Standard international symbols used on a meter may differ from the symbols used on wiring or schematic diagrams. For example, the international symbol for a battery on a meter is not the same as the symbol for a battery in a schematic diagram. International symbols require less space on the meter and provide quick recognition regardless of language. All meters use terms to describe displayed information. Understanding meter terminology is required for proper meter use. For example, a meter may display an electrical quantity as an average, effective, peak, or RMS value. The difference between each value must be understood to correctly interpret the measurements. Electrical prefixes. In the electrical field, numbers are commonly used when taking measurements, designing circuits, specifying equipment, and troubleshooting. Numbers used in the electrical field typically range from very large numbers to very small numbers. In order to simplify larger and smaller numbers, metric prefixes are used. Prefixes can be used with any electrical quantity, such as 1 kilovolt or 1,000 volts, 1 kiloamp or 1,000 amps, 1 kiloohm or 1,000 ohms, or 1 kilowatt or 1,000 watts. The most commonly used prefixes in the electrical and electronic fields are mega, represented by a capital letter M, kilo, represented by a lowercase letter k, milli, represented by a lowercase letter m, and micro, represented by the Greek letter mu. Converting units. To convert a base unit number that does not include a prefix to a unit that includes a prefix, the decimal point in the base unit number is moved to the left or right and a prefix is added. For example, to convert the base number 825,000 watt-hours on an electric bill to kilowatt-hours, the decimal point is moved 3 places to the left and the prefix kilo is added to the number. Thus, 825,000 watt-hours is equal to 825 kilowatt-hours. Likewise, to convert the base number 0.033 amps to milliamps, the decimal point is moved 3 places to the right, and the prefix milli is added to the number. Thus, 0.033 amps is equal to 33 milliamps. Electrical units such as resistance, voltage, and watts are often measured in large values. Typical prefixes used with large electrical values are kilo and mega. To convert larger numbers to simpler terms, the decimal point is moved to the left and a prefix is added. For example, 150,000 ohms equals 150 kiloohms. 1,000,000 ohms equals 1 megaohm. 1,500,000 ohms equals 1.5 megaohms. Electrical units such as amps are often measured by values less than a whole unit or less than 1. For units less than 1, the prefixes milli, micro, nano, and pico are used. To convert smaller numbers to simpler terms, the decimal point is moved to the right and a prefix is added. For example, 0.005 amps equals 5 milliamps. 0.000008 amps equals 0.008 milliamps. 0.0005 amps equals 500 microamps. Digital displays. Digital multimeters display readings as exact numerical values. Analog meters indicate values by the mechanical motion of a pointer moving across a scale. The exact numerical values displayed on a digital multimeter eliminate errors which can occur when reading an analog meter. The exact numerical value on a digital display is determined by the number displayed, the position of the decimal point, and the prefix used. A range switch is pressed to change the range and placement of the decimal point. If the range is not high enough, the meter will read an overload, or OL, or automatically adjust to a higher setting. Meters that automatically adjust the range are referred to as auto-ranging meters. All meters have a specified range for each electrical quantity measured. For example, typical voltage ranges on a digital display are 3 volts, 30 volts, 300 volts, and 1000 volts. The highest possible reading with the range switch set on 3 volts is 2.999 volts. The highest possible reading with the range switch set on 30 volts is 29.99 volts. The highest possible reading with the range switch set on 300 volts is 299.9 volts. And the highest possible reading with the range switch set on 1000 volts is 1000 volts. Voltage ranges vary with the meter used and are chosen for the best resolution. For example, a 9.672 voltage level could be read using the 40 volts, 400 volts, or 1000 volts range. This voltage level would be displayed as OL on the 4 volts range, 9.672 on the 40 volts range, 9.67 on the 400 volts range, and 9.6 on the 1000 volts range. Bar graph. The bar graph on the DMM shows changes and trends in a circuit. The advantage of the bar graph is that the reading is updated faster than the digital reading. The bar graph is commonly used when quick-changing signals cause the digital display to flash, or when there is a change in the circuit that is too rapid for the digital display to detect. For example, mechanical relay contacts may bounce open when exposed to vibration. Contact bounce causes intermittent problems in electrical equipment. The quick response of the bar graph allows easier detection of most contact bounce problems. Movement of one or more segments the moment the contact opens indicates contact bounce. DMMs can have a non-wraparound or wraparound bar graph. The range of a non-wraparound bar graph is equal to the range setting of the digital display. For example, if the digital display is set on the 30 volts range, then the bar graph displayed will also have a range of 0 to 30 volts. 23 segments displayed in the 30 volts range indicate a 23 volt reading. A wraparound bar graph is a bar graph that displays a fraction of the full range of the graph. The pointer wraps around and starts over when the limit of the bar graph is reached. For example, in a display reading 25 volts, the pointer has wrapped around twice, 20 volts, and points to 5 volts. The advantage of a wraparound bar graph is that the total range of the bar graph is divided into many more segments. This provides greater sensitivity and accuracy when monitoring changes using the bar graph. Ghost voltages. A DMM set to measure voltage may display a reading or ghost voltage before the meter is connected to a powered circuit. Ghost voltage is voltage that is not connected to a powered circuit and appears as changing numbers on the display. Ghost voltages are produced by magnetic or electrostatic fields generated by current-carrying conductors, fluorescent lighting, and operating electrical equipment. Ghost voltages enter a meter through test leads not connected to a circuit. The test leads act as antennas for stray voltages. To ensure true circuit voltage readings, connect the DMM long enough until a constant reading is displayed and turn off nearby sources of power that may cause ghost voltages. Measuring AC voltage. When testing AC circuits, voltage readings are taken. Voltage readings indicate the presence or absence of voltage and the voltage level. A voltmeter is used when exact voltage values are required. An AC voltmeter is used to measure AC voltages. The AC voltmeter is connected directly across the part of a circuit requiring measurement. To measure AC voltages with a voltmeter, apply the procedure 1. Set the function switch to AC voltage. If the voltage in the circuit is unknown, select the highest setting if the meter has more than one voltage range. 2. Plug the black test lead into the common jack. 3. Plug the red test lead into the voltage jack. 4. Connect the test leads to the circuit. The position of the test leads is arbitrary. Common industrial practice is to connect the black test lead to the grounded or neutral side of the AC voltage. 5. Read the voltage displayed on the meter. Measuring DC voltage. When testing DC circuits, voltage readings are taken. Voltage readings indicate the presence or absence of voltage and the voltage level. A DC voltmeter is used to measure DC voltages. The voltmeter is connected directly across the part of a circuit requiring measurement. To measure DC voltages with a voltmeter, apply the procedure 1. Set the function switch to DC voltage. Select a setting high enough to measure the highest possible circuit voltage if the meter has more than one voltage position or if the circuit voltage is unknown. 2. Plug the black test lead into the common jack. 3. Plug the red test lead into the voltage jack. 4. Discharge any capacitors. 5. Connect the meter test leads in the circuit. Connect the black test lead to circuit ground and the red test lead to the point at which the voltage is under test. Reverse the black and red test leads if a negative sign appears in front of the reading on a digital meter. 6. Read the voltage displayed on the meter. Resistance. Resistance readings are taken to determine the condition of a component or a non-powered circuit. Resistance can range from 0 ohms to infinity. Based on the expected reading of the component tested, one of two different meter settings can be used. The continuity setting can be used to check components such as fuses that typically only read 0 ohms, good, or infinity, open. The resistance, omega meter setting, can be used to check components that have a resistance somewhere between 0 ohms and infinity. The continuity setting is used to indicate an open or closed circuit with the power off. To test for continuity, the meter is set to the audio beeper setting. The meter leads will produce a sound when connected together. The continuity setting is commonly used to test removed fuses, switches, contacts, and other components that typically indicate a very high or very low, if any, resistance reading. Measuring resistance. Resistance readings are always taken when all power is removed from the circuit or the component tested is removed from the circuit. When measuring resistance, the meter supplies power through batteries inside the meter. Caution: ensure that no voltage is present in the circuit or the component tested before measuring resistance. Low voltage applied to a meter set to measure resistance causes inaccurate readings. Voltage above the protection limit applied to a meter set to measure resistance can cause meter damage. Check for voltage using a voltmeter. To measure resistance using the resistance setting, apply the procedure: 1. Check that all power is off in the circuit or component under test. 2. Set the function switch to the resistance position, which is marked with the symbol omega on digital meters. 3. Plug the black test lead into the common jack. 4. Plug the red test lead into the resistance jack. 5. Ensure that the meter batteries are in good condition. The battery symbol is displayed when the batteries are low. Digital meters are zeroed by an internal circuit. 6. Connect the meter test leads across the component under test. Ensure that contact between the test leads and the circuit is good. Dirt, solder, flux, oil, and other foreign substances greatly affect resistance readings. 7. Read the resistance displayed on the meter. Check the circuit schematic for parallel paths. Parallel paths with the resistance under test cause reading errors. Do not touch exposed metal parts of the test leads during the test. Resistance of your body can cause reading errors. 8. Turn the meter off after measurements are taken to save battery life. Measuring current. Measuring current flow is very useful when troubleshooting. Equipment and circuits that are drawing more than the rated current are overloaded or have a problem. For example, insulation breakdown is one circuit condition that causes a higher current flow. Equipment that is drawing less than the rated current is underloaded or may also have a problem. For example, slipping belts connecting a motor to a driven load causes less work required by the motor, resulting in a reduction in current drawn. Two methods used to measure current are inserting an inline ammeter in the circuit or using a clamp-on ammeter. The inline ammeter is used for currents that are less than the maximum current rating of the meter. Both methods are used when measuring AC or DC. An inline ammeter measures current in a circuit by inserting the meter in series with the component tested. Inline ammeters are primarily used when testing smaller electronic components. A clamp-on ammeter is a meter that measures current in a circuit by measuring the strength of the magnetic field around a conductor. Clamp-on ammeters measure currents from approximately 1 amp to 1,000 amps or more. Clamp-on ammeters are the preferred method of taking current measurements because they do not require an opening of the circuit. However, clamp-on ammeters are not as accurate as inline ammeters. Inline ammeters are limited to currents less than 10 amps and are not practical for measuring most industrial current levels. The reading indicates the amount of current drawn by loads connected to the conductor. Clamp-on ammeters measure the current in a circuit by measuring the strength of the magnetic field around a conductor. Care must be taken to ensure that the meter does not pick up stray magnetic fields. Whenever possible, separate the conductors under test from other surrounding conductors by a few inches. To measure AC using a clamp-on current probe accessory, apply the procedure: 1. Set the function switch to AC current. Select the proper setting to measure the highest possible circuit current if the meter has more than one current position or if the circuit current is unknown. 2. Plug the current probe accessory into the meter. 3. Open the jaws by pressing against the trigger. 4. Enclose one conductor in the jaws. Ensure that the jaws are completely closed before taking readings. 5. Read the current displayed on the meter. Ohm's law. Ohm's law is commonly used in the electrical and electronic fields. Ohm's law states the relationship between voltage, current, and resistance. Any value in this relationship can be found using Ohm's law. Using the formula listed in a chart form, the unknown value is covered. Values that are next to each other are multiplied. Values that are over each other are divided. Ohm's law states that current in a circuit is directly proportional to the voltage and inversely proportional to the resistance. To calculate current, apply the formula current equals voltage divided by resistance. Ohm's law states that voltage equals current times resistance in the circuit. To calculate voltage, apply the formula voltage equals current times resistance. Ohm's law states that resistance in a circuit is equal to the voltage divided by the current in the circuit. To calculate resistance, apply the formula resistance equals voltage divided by current. Ohm's law is used to predict what will happen in a circuit before power is applied when two of the three electrical values, E, I, or R, voltage, current, or resistance, are known. The predicted value is used to size conductors and equipment to determine the best voltage level to use and to prevent potential problems before they occur. Ohm's law is also used when troubleshooting to determine how a circuit should be operating and how it is operating under power. For example, when the insulation of equipment or conductors breaks down, resistance in the circuit will decrease and current will increase. By measuring a current level higher than normal, the troubleshooter knows that the circuit resistance has decreased or the circuit voltage has increased. This information can be used to determine potential problems such as insulation breakdown or a high voltage condition. Likewise, if in the same circuit the measured current level is lower than normal, the troubleshooter knows that the circuit resistance has increased or the circuit voltage has decreased. This information can be used to determine potential problems such as dirty switch contacts, loose connections, or a low voltage condition. Power formula. The power formula states the relationship between voltage, the force that causes current flow, current, the movement of electrons, and power, the rate of using energy in an electrical circuit. Any value in these relationships can be found using the power formula. Like Ohm's law, the power formula is used to predict what will happen in a circuit before power is applied and when troubleshooting. As long as two of the three electrical values, power, voltage, or current, are known or measured, the third value can be found. The power formula is especially useful when determining expected current values, as most electrical equipment lists a voltage and power rating. The listed power rating is given in watts for heating elements and most appliances, or in horsepower for motors. Power is the rate of doing work or using electrical energy. True power is measured in watts. The power formula states that the power in a circuit is equal to the voltage times the current in a circuit. To calculate power, apply the formula power equals voltage times current. Current is the amount of electrons flowing through an electrical circuit. Current is measured in amperes. The power formula states that current in a circuit is equal to the power divided by the voltage in the circuit. To calculate current, apply the formula current equals power divided by voltage. Voltage is the amount of electrical pressure in a circuit. Voltage is measured in volts. The power formula states that voltage in a circuit is equal to the power divided by the current. To calculate voltage, apply the formula voltage equals power divided by current. Testing diodes. A diode is an electronic device that allows current to flow in only one direction. A diode has an anode and a cathode. To test a diode, apply the procedure 1. Connect the test leads to the meter. 2. Set the meter to diode test. 3. To test a diode in a forward-biased condition, connect the red test lead to the anode and the black test lead to the cathode. The forward bias reading is displayed. The reading should be 0.2 to 0.8 volts. 4. To test a diode in a reverse-biased condition, connect the red test lead to the cathode and the black test lead to the anode. An infinity resistance or overload is displayed. The diode is bad if the meter readings are the same in both directions. This video is one of several training products featuring Fluke test tools available from American Technical Publishers, Incorporated. Related information can be obtained by visiting the American Tech website at www.americantech.org or calling American Tech at 1-800-323-3471, or by visiting the Fluke website at www.fluke.com, or by calling the Fluke Corporation at 1-800-443-5853. American Technical Publishers